Hi, welcome to our 8 a.m. press conference, Global Impacts of the 2015 to 2016 El Niño. Our speakers will be Dwayne Walliser, Chief Scientist, Earth Science and Technology Director at NASA Jet Propulsion Laboratory, Marty Herling, Research Meteorologist, NOAA's Earth System Research Laboratory, Mark Olsen, Research Scientist, Morgan State University and NASA Goddard Space Flight Center, and Jim Randerson, Earth System Scientist at the University of California, Irvine.
Thank you for the introduction, and thank you all for coming to hear my colleagues and I present our research on El Niño. The two globes in this slide are just meant to provide some context for today. The upper left one is a depiction of the sea surface temperature anomalies in the Eastern Pacific, and you can see the signature of El Niño, the warming Eastern Pacific. The lower right one highlights the impacts on the extratropical circulation from El Niño. And it's just meant to highlight for this session that the El Niño has ramifications far removed from the tropical Pacific and produces impacts far and wide, a number which will be highlighted in this session. The research that I'm going to present is on the El Niño effects of atmospheric rivers, storms that many of you may be acquainted with or are important to California. It's been carried out by myself and my colleague Bin Guan, who's sitting here in the front. And so for those of you that may be less acquainted with atmospheric rivers, the visualization experts at Goddard Space Flight Center produced this very nice animation that I'm going to show you. It's a depiction of an atmospheric river, and it loops 4 different times, twice from this global perspective, and then it zooms in. And the, let me see if I can get it going. Oops. Play. There we go. So the colors from blue to near white are increasing amounts of water vapor, and the white are clouds, and the brilliant colors are precipitation up to about 1 inch per day. And you can see this atmospheric river there forming to the left, and as it comes in, it approaches California, and then right when it hits landfall, you can see an extreme amount of precipitation. It's going to loop one more time. You can see the river of moisture flowing in, hitting the coast, and then producing a lot of precipitation at landfall. And so to look at that landfall, what happens at landfall more specifically, this is a cartoon illustration of that. What you see is on the left, atmospheric river, this river of moisture impinges on the coast. It's forced up over the smaller coastal range and the larger Sierra range. And when it does that, the air cools, it condenses, it forms clouds and heavy precipitation in California and in this region. And overall, when that happens, atmospheric rivers account for 2 very important things for California. They account for about 40% of California's water supply in only about 10 storms like this. And they're also responsible for most major flooding events. And so that's the reason why we study them and we learn how to better model and predict them. And so Bin and I's research, we have an interest in sort of globally characterizing atmospheric rivers, and for the purposes of understanding their impacts globally, and also for doing model and forecast evaluations. And so a component of the paper that we're presenting on Friday is the development of a detection algorithm to detect atmospheric rivers where they occur for a multi-year, more than a decade data set. And the results on this slide are a climatology, the first global climatology of atmospheric rivers. And the color shading represents the frequency of occurrence of atmospheric rivers, up to 0 to about 12%. So where it's red, say in the mid-latitude regions, particularly over the ocean basins, you can get up to an atmospheric river occurring about once in every 8 to 10 days. And the vectors that you see there are the directions that they transport moisture. And so the poleward components of those vectors are important for the global distribution of moisture and precipitations, particularly in high latitudes. And the eastward components are important to the landfall consequences that I just mentioned in terms of hitting the coastlines. And so with this information in this global data set, which is essentially a chronology of atmospheric events for over a decade, we can do things like study where atmospheric rivers make landfall globally. And so this map is a depiction of how often atmospheric rivers make landfall over the globe, over the coast, and you can see that there are many landfall events that occur in North America and South America on the east, on the west coast, and also in the European sector. But overall, they make landfall virtually on every continent and even in very high latitudes. Another thing we can do with this climatology is look at the impacts of El Niño on these very important storms for our West Coast region. The upper right figure is still the climatology that I just mentioned, and the big map there is the modulation that typically occurs during El Niño to the spatial distribution of these storms. And so remember the map was 0 to 12% on the upper right, which is a typical amount that occurs. And the modulations due to El Niño, you can see, are minus 6% to plus 6%, so there's significant amounts relative to the mean. And you can see a lot of modulation, but in fact, near the West Coast in California, there's very little impact on the frequency of atmospheric rivers due to El Niño based on these results. However, if you look at the impact on the actual precipitation of the atmospheric rivers, there is an impact. On the left side is the typical amount of rainfall that you get from atmospheric rivers of the California region. And so you can see from about 0 to 15 millimeters today, especially in the Northern California region. That's the amount of precipitation you might get from an atmospheric river in a typical year. And on the right is conditions, how El Niño influences that condition. And you can see just positive values in red colors, which means that El Niño enhances the rainfall characteristics of a given El Niño. So we might not get more atmospheric rivers, but any given river would be stronger in terms of precipitation. And the last slide, and the third effect that I want to illustrate, is that in coming with El Niño, conditions are typically warmer than normal. And so on the left, it shows that El Niño atmospheric rivers are slightly warmer, and because of that, their rain to snowfall ratio is slightly higher in that they typically produce more rainfall and produce less snowfact. And in the interest of time, I'm going to not describe that in great detail and just move on to my summary slide. So the importance and why we care about atmospheric rivers and study them, particularly in the West Coast and in California, they provide about 40% of our annual precipitation in only about 10 storms. They're responsible for most major flooding events. And then the work that we came to discuss here this week at AGU is the impact of El Niño on these atmospheric rivers, and our results show that El Niño doesn't necessarily impact the frequency of events that will happen in California. However, for any given atmospheric river event, it is usually wetter, stronger precipitation, but more in the form of rain than snow. Thank you. Pass it to my colleague, Marty.
Thank you, Dwayne. I'm going to carry on this theme a little bit on the California impacts in particular. And what I'm going to share with you is a paper which I think was released here during the AGU. The lead author is Andy Hoyle, and it's a collaboration between scientists at the University of Colorado in Boulder and NOAA at your System Research Laboratory. And the question that's really on the tip of many people's tongues is whether this El Niño is going to be a drought buster. This is a time series showing the annual precipitation, the wet year, November to April, from 1895 to 2015, indicating where there's green bars, wet years for California, statewide averages, and where you see the tan bars, dry years. And there's asterisks on top of those bars. There's about 25 or so asterisks indicating the historical occurrences of El Niño years. And one of the interesting things that speaks to the checkered history that El Niño has had on California precipitation is that two of the wettest years were the very strong El Niños of 1982-83 and then 1997-98. Many of you know those years. But maybe what we had forgotten was that the two driest years in the historical record were also El Niño years. And so therein lies the checkered history and the challenge that we have as scientists to sort out what the current very strong El Niño may mean for California precipitation. And I put a circle around the last 4 years. We've had 4 years of drought. It's the driest 4 consecutive years on a record since 1895. And we've accumulated in the state about 1 year's worth of deficit. And so the question is whether we can recover from a simple accounting point of view 1 year's worth of precipitation with a strong El Niño. So to tackle that question as to whether we could recover from 4 years of drought with one strong El Niño, what NOAA scientists and our colleagues have done at the University of Colorado is to perform a set of climate simulations in which we've recreated a historical record of climate variability using climate models, one from a NOAA climate forecast system, one from a European Center model framework. And I'll share those results with you in just a moment. We repeat these experiments many times so that we create more than just 2 strong El Niño environments, but rather hundreds of them. This allows us to speak to a statistically robust impact that we can't infer from just a brief historical record. I'll share that with you. We'll compare the effects of a strong versus a weak El Niño, and then we'll take a look at the cumulative effects of the past 4 years of the ocean's impact on California rain against the average effects that a strong El Niño would have. And I'll show this to you next with some animations. So what you're going to see here is a time series of the daily precipitation accumulated on the left top for a strong El Niño situation, and on the top right for the average of the 4 years of drought that we've just experienced, the ocean influence. There's 2 lines evolving through time. The blue one is for the El Niño situation, and the red one is for the average of the 4 years of the drought we just experienced. This is a simulation from the NOAA model. I'm going to show you this again now for the European model. It'll show the same story. The point being is that there's very different effects that the strong El Niño has than the effect that we've experienced for the last 4 years. In other words, the ocean has changed, and the way it's changed matters substantially for California expectations of rain. Here's the same animation from the European Center models that we also ran at NOAA and the University of Colorado. So you can see the bifurcation between the blue and the red lines indicating that El Niño begins to distinguish itself from the cumulative rainfall departures during the previous 4 years. That split happens around now. So the fact that we haven't yet experienced particularly heavy rains or an abundance of rains for the state should not be viewed as an El No-show. The distinction becomes more evident in the coming weeks as we move into the holiday season and into early January. Now, it's not a certainty. We ran hundreds of these simulations, so one of the aspects is to speak to the probability. Here's an analysis that is a histogram. That black curve is the frequency of occurrence of wet or dry winters for California when the ocean is in its normal condition. So the expected value is about 100% of normal climatological situation. Using our model data for the weak El Niño environment, we don't see too much sensitivity. This is actually a Central California analysis centered around San Francisco into the eastern Sierras. And basically, the effect of weak El Niños is not to greatly alter the risk of wet or dry. Then this is our model simulations for the strong El Niño. So you can really see in this red curve how you shift the odds to an increase in wet probability. Now the average expectation is about 150% of normal, which is half again of the typical climatology. And if you're looking for the 200% of normal odds, which would recover in an accounting sense, that risk increases 5-fold for Central California. So just to summarize this very, very briefly, a few takeaway points. Is El Niño a California drought buster? Well, despite the checkered history that El Niño has had on California rainfall for the last 120 years, strong El Niños do greatly increase the odds of wet conditions for the state. That's good news. The bad news is these rains can come in abundance, and they can be heavy, and Dwayne talked about the atmospheric river sensitivity. The models confirm that the near record wet winters that happened in 82, 83, and 97, 98 were not just random, but were strongly influenced by those El Niño situations. And lastly, a dry California winter in this upcoming year, it's not an impossibility. So I don't want to say this is 100% certainty. I'm not going to bet the farm on it. And NOAA has official seasonal forecasts that are couched in probability language. But the odds have greatly shifted to being very wet this upcoming winter. So you've had 2 overviews of California, and now we're going to get a global view on the effect on El Niño and ozone in the middle latitudes from Mark Olsen.
Thank you, Marty. I'm going to be switching gears to ozone, as he said. So in general, why do we care about tropospheric ozone? Now, ozone's important to air quality. It is a pollutant near the surface. It's also a greenhouse gas in the troposphere, and it plays an important role in tropospheric chemistry. Now, it has both natural and human sources, so there's really a need that we have to understand the sources of the natural variability in order to assess the human influence. Now, in our study, we take a look at the tropospheric column ozone, and that is, it's the total amount of ozone between the surface and the top of the troposphere here. So it's not ozone at a specific level, it's not surface ozone, so there's also not a direct bearing on the air quality in these results. So we use ozone data from the ozone monitoring instrument and the microwave limb sounder. Both these are on board NASA's AURA satellite. We incorporate the data into the NASA GEOS-5 atmospheric model. And this combination of the AURA data with the model allows us this first comprehensive analysis of the mid-latitude impact of El Niño on tropospheric ozone. Previous studies have shown a strong response of ozone in the tropics to El Niño through both chemistry and dynamics, and that's pretty well known. The impact on mid-latitude ozone is not as well understood. So we find changes in the study to mid-latitude tropospheric ozone in response to both El Niño and La Niña. And these changes, these patterns of positive and negative changes, are consistent to changes with the winds. So a measure of this response is the change in ozone per degree change in the tropical Pacific Ocean temperature, the sensitivity of ozone to the sea surface temperatures. And on this plot of the sensitivity, the blue shades here represent less ozone with El Niño. The red shades indicate more ozone with El Niño. And as you can see, there's this large tropical response there. And as I said before, that's fairly well known. However, I want to focus on the mid-latitudes, and here I'm just going to blow up this area of the over North America and the Pacific and Atlantic here. And you can see the negative sensitivities are the blue, and this hot spot here over the United States. The El Niño is known to impact and change the global wind patterns. So I'm next going to take a look at the wind patterns, the differences between months of strong El Niño minus the months of strong La Niña. And this is at the top or near the top of the troposphere. I'm going to overlay these on top of the sensitivity. And you see these anomalous circulations here, and they correspond quite well with the patterns of the sensitivity. And you can see that for instance, here over North America, this counterclockwise, or over the U.S., this counterclockwise circulation here, or cyclonic circulation, anomalous circulation here, will tend to produce dynamically an upward increase in the upward motion. This is going to serve to reduce the column ozone. Now, these patterns in the corresponding of the winds and the sensitivity are pretty typical throughout the mid-latitudes in both the northern hemisphere and the southern hemisphere. Now, there are a lot of factors that really impact the amount of tropospheric ozone. So one thing we actually do want to know is how much of this is due to El Niño. And so this figure here actually shows the percent variability or variation in ozone that's actually caused by or due to El Niño. And you can see once again that this hot spot in the tropics, like said many times here, it's well known, but in the extratropics, in the mid-latitudes, the response or the percent variability that's explained is weaker, but you can see these hot spots here, for instance, right over the United States and South Africa here, where about 20 to 25% of the variability is explained by El Niño. And with this 20 to 25% and the sensitivity is large enough that we do need to consider this when attributing causes to long-term trends and so forth. So with that, I'm just going to throw the results slide back up here, and I'll turn over the microphone here to Jim, who'll lead a discussion on the fires.
Thank you, Mark. I'm going to discuss the influence of the current El Niño on the global pattern of fires. I'd like to acknowledge my co-authors, Yang Chen and Doug Morton, who are in the audience. And this work will be, the science foundation for this work will be presented on Thursday by Yang Chen on a session on global biomass burning. So I've had the opportunity and to participate and contribute to an international collaboration to map out the pattern of global fires, what's known as the Global Fire Emissions Database Project with international collaborators. And our goal is really to understand how human and environmental controls are changing fires worldwide. And so this is a time series of global burned area from the GFED database. And what's shown here is at a quarter degree, the fraction of each quarter degree cell that's burned. And the data are derived and created from 2 NASA satellites, Aqua and Terra, at a 500-meter resolution, and that's aggregated to the resolution that you see. And what I'd like to draw your attention to here is that the burning on the perimeter of tropical forests. So across Indonesia, across the Congo, and the forests of South America and Central America, fires burn to the edge of the forest. Many of these fires are ignited in an agricultural context, and they're extinguished as the fires move into the more moist forests. And what's important to recognize is that during drought years, these fires, there's no longer a limit to the movement of these fires into tropical forests. So the fires expand, they increase the burned area in forests, killing more trees and contributing to the buildup of atmospheric carbon dioxide. So fires, anthropogenic fires, are a threat to tropical forests. And so using this GFED time series, we've been able to look at the influence of climate and El Niño on global patterns of fires. And so what we find is that there are several areas around the world where El Niño has a large influence on fires in peatlands and tropical forests, including in Indonesia. And so what's shown here is the time series of burned area from 1997 to the present, and areas that are shown in orange are existing El Niños, including the very strong 97-98 El Niño. And you may have seen some of the press over the last month that the burning in Indonesia has actually exceeded all the years in our time series except for 97 and 98. So there's extensive burning, created a large air quality issue in Indonesia and equatorial Asia. And the emissions there have substantially amplified deforestation and land use fluxes for this year. Because of the way that El Niño unfolds with teleconnections, the threats are not over. So we move into 2016. We expect threats to tropical forests in Southeast Asia, where the fire season peaks in March. And then in Central America, so there's a shift as well from Asia then to the neotropics and to South and Central America, where, as you can see, in the 97-98 El Niño, there was extensive burning through southern Mexico, Guatemala, and many countries in Central America. And so we expect a threat and a risk to forests in May. And then to the southern Amazon forests, actually, as far as next August through October. And really, in the southern Amazon, it's a combination of El Niño and the North Atlantic that controls the fire behavior, but El Niño is a major risk factor. So the foundation for why these fires increase is really the balance of moisture. This is another NASA product that shows, it's from NASA's twin satellites of the gravity recovery and climate experiment. And what's shown here is the anomaly of terrestrial water storage. It's the amount of moisture in soils and in reservoirs. And brown shows a lower soil moisture level, and blue shows a positive moisture balance. And as you move into, this is from September of 2015, we see depleted moisture in the forests of Indonesia, and that allowed the fires to expand. And we're also seeing a growing reduction in moisture across the Amazon, and this is the threat then for 2016 from the perspective of wildfires. And these time delays associated with the fire response to El Niño are actually amplified by biosphere-atmosphere feedbacks. And this is a diagram for the Amazon showing right now we're in the wet season, but if there's less rain that occurs now during the wet season when the teleconnection with El Niño is strongest, then the moisture in the root zone of the forest is lower. So coming into the end of the wet season, we expect to have less moisture available to support the forest during the dry season. So then there's less transpiration and evaporation of moisture by the forests during the dry season. This lowers the humidity, it lowers the fuel moisture, and so fires can more easily spread through the understory, killing trees and leading to losses of carbon. So in conclusion, this time series derived from NASA, multiple NASA satellites, allows us to study fire and human controls on allows us to study human and environmental controls, climate controls on the global pattern of fires. Fire emissions from Indonesia were exceptionally high during September to October of this past year. The emissions actually exceeded the fossil emissions from Indonesia and Germany. And this was covered very nicely in a blog by Guido van der Werf, one of my GFED colleagues. And then the punchline from my presentation here is that we really expect, because of the El Nino teleconnections, increased threats for forests across Central America and South America in 2016, moving from the spring to the summer. Thank you.
Thank you.
So I think we're going to conclude our briefing, and we'll have the results slide summary here, and we're open to questions, I think, correct?
Thank you. We'll now take questions from any reporters in the audience. If you could please raise your hand and state your name and affiliation. Thank you.
Hi, Kit Stoltz for Dr. Hurling. You said, you alluded to more rainfall later in the year, I guess February to April. Can you expand on that a little bit?
See if that's on. Good. Well, historically, the bulk of precipitation in California doesn't really accumulate until begin accumulating until mid to late December, and then, of course, continuing through March. The indications of what the annual total will look like from December is not very reliable. So really the abundance of rain, especially as you move southward in the state, really begins kicking in January and even February in San Diego County areas. So some of those very heavy rains that can be very destructive, landslides and so forth. And what with the drought that we've had, the ground situation is going to be not very conducive for infiltration. Runoff and erosion and potential mudslides and loss of property are really going to be elevated in that area as we go later into the rainy season.
Hi, Irene Klotz with Discovery News. So can you take a stab at answering your question, Dr. Hurling, about whether 1 year of a strong El Nino will cancel out the accumulated drought in California?
Yeah, one of the interesting things about what the model experiments that NOAA's been doing indicates is even in normal years, there's an enhanced risk of that we call a heavy tail. There's an enhanced risk of having a heavy rain winter in California. The average is actually less than normal. The typical winter would be slightly drier. What El Nino does is it really ramps up that tail risk, and so the tail risk is increased by about 4 or 5-fold. We were looking at about 1 year's worth of deficit accumulated in the last 4 years. So there is a 5-fold increase this year of recovering that. But it's too simplistic to talk about drought busters as being just about rain. So you have soil moistures and groundwater that has been depleted over decades that isn't going to be recovered no matter how much it rains. So there's a water resource challenge in the state that goes beyond just having a very wet dousing rain this year. It's very important to keep that in mind. The reason really that the rains that would fall in a strong El Nino are of concern is that the reservoirs have to be managed very intensely. You have to vacate these reservoirs when the heavy rainstorms come to anticipate the next storm. So water resource managers have their hands full in dealing with the rains at hand, let alone 200% of normal.
Thanks. And also, I was wondering if either you or Dr. Weiser could address the effects of El Nino or atmospheric rivers in other parts of the country. There's been quite a warm belt going through the Northeast. We've had 85 degrees in Florida in December. Are these, from these atmospheric rivers or from El Nino or just for some other reason?
So I'll just add that the impact of atmospheric rivers is mostly on the West Coast. It's where they occurred naturally, and the influence of El Nino would be on the West Coast or not. So I can't really address your question with respect to the rest of the country, but you can take a stab at the climatological aspect.
I bet Mark and Jim would like to answer that question. What do you guys think? It has been warm in the east, but it's not uncommon that in an El Nino winter, and if you look at the NOAA seasonal forecast for temperatures for winter, the eastern third to half of the U.S., the Northeast in particular, are expected to be much above normal temperatures, several degrees Celsius above normal, 4 or 5 degrees Fahrenheit warmer than normal. 82, 83, 97, 98 winters were very warm in the Northeast and in the northern U.S. So seeing the lack of cold air is a symptom of El Nino, of a strength of the type that we're having.
This is Mary Miller from the Exploratorium. I have a question about the effects of El Nino whether it's amplified by the unusual warm water, the blob we've been having for the last year and a half, what ideas there are. Maybe it's a climatological averaging or atmospheric river, but very interested in whether they compound each other, offset each other. What do you think the impacts are?
I'd like to know the answer to that question too, and I'm kind of wondering what Marty or my other colleagues might say. I don't know, but I've been curious myself, and I suspect the NOAA folks talk about that a lot, and so.
Just as a slight segue for a moment, NOAA is engaged in an El Nino rapid response this winter. They are flying aircrafts into the tropics out of Hawaii later in January, February, to sort of almost like Hurricane Hunter style, if you will, to be in the field, taking measurements to understand the way the ocean and atmosphere system are unfolding in this situation. So, but you asked a question about this warm patch that had developed over the last 4 years in the North Pacific. It was very much a symptom of this area of high pressure, which I think Mark touched on a little bit also in terms of the circulation patterns. This high pressure, this resilient ridge that led to the drought of 4 years, leaves a footprint in the ocean, and that footprint is one of warmth underneath it. So it's a symptom more than a cause. We're not 100% sure how much its residual effect will be on this upcoming winter. But the warmth that really matters this year is the warmth that's on the equatorial Pacific. We're very confident that the temperatures are running 3 degrees Celsius or so above average. There's a monitoring system called the Toga Tau Triton Array System that is moored, has been there for about 30 years. So we know it's unusually warm at the caliber of 82 and 97, and that's really what matters to us in California right now.
I think we have a question from the chat.
Yes, thank you. This is from Brian Kahn of Climate Central for Jim Randerson. Could carbon emissions from Amazon fires next year be comparable to emissions from Indonesia fires this year?
See, that's a really good question. I think one thing I'd like to point out with respect to the Amazon is that El Nino is a risk factor. It's a risk for the northern Amazon in the spring, and then for the southern Amazon next late summer and fall. And the emissions from Indonesia, in some ways, they've been extensive on the order of from preliminary estimates of 0.2 to 0.3 petagrams of additional carbon that have been emitted. In past strong Amazon drought intervals, including 2005 and 2010, the anomalously high fire emissions have been of that magnitude. And so it's possible, but again, the Amazon is controlled not only by the by El Nino, which is a risk factor, but it's also by the North Atlantic. So it'll really depend on how the North Atlantic evolves over this spring and early summer, and that will really influence then the intensity of the dry season and fire risks in the Amazon.
Thank you very much.
Go ahead.
Hi, Ros Pidcock from Carbon Brief. It's another question for Jim Randerson. On a related note, actually, so with the El Nino teleconnections, you said you expect an increased risk of fires in Southeast Asia, Central America in 2016, on top of what we've seen in Indonesia. Does that mean, do you expect the total CO2 emissions associated with fires during El Nino to exceed those in 97, 98?
So far, the Indonesian emissions were lower, and so I think we're looking at a comparable event, but because our time series is relatively short in an Earth system context, 18 years, it's difficult for us to say whether it will be it'll exceed the 97, 98 El Nino. Right now, it looks like it'll be comparable, but not necessarily exceeding. But it really depends on many factors and how the teleconnections unfold over the next 6 months.
This is Molly Michelson from Science Today. Another question for Jim Randerson. We heard this late summer that maybe some of the California fires were caused by El Nino, the California wildfires. Could you comment on that?
The attribution of wildfires in California is challenging, and there's a number of researchers that are beginning to work on this. I can't actually speak to whether there's an El Nino connection for the California wildfires. We saw really intense fire activity in Northern California in late summer, and some of the fire behavior exceeded or is comparable to what we see typically in Southern California near U.C. Irvine with the Santa Ana fires. But the El Nino link, from our research, we've been really looking at these patterns across very broad regions, and I don't know if there's a strong attribution of California fires directly to El Nino or other climate modes.
Are there any other questions from reporters in the room? Any other questions from the chat? No? Okay, thank you. That concludes our 8 o'clock press conference. Next up at 9 o'clock, the Arctic report card.